Hello everyone, welcome to Digital Lesson for Students by Department of School Education, Nagaland. I am T. Punguri, MSc MPhil Mathematics, your maths tutor from CD King Higher Secondary School, Jotsama, Kohima. This is exam season, so everyone will be looking for this chapter, Calculus, Differentiability. So here we are going to learn this differentiability. You have studied a little bit in class 11, that is just a basic. You have studied about limits and a little bit of differentiability. So we are having a small recap here with the limits, continuity, then we will start with our differentiability. Okay, what is a limit? Limit. Suppose there are 2 points A and B. A car starts at this point at time t. The car starts at this point at time t. It can reach this place at t1. T1 time, isn't it? So the T1 is moving towards, approaches or tending towards this T1, isn't it? So in that case, what will happen to its distance? Distance, T is an independent variable, we know, but distance depends on the time, therefore this is a dependent variable, right? When T approaches T1, what will happen to this distance? The distance will be moving towards 0, right? It will go nearer and nearer to 0. So when T approaches T1, this distance will approach 0. So d of t approaches 0 as t approaches T1, right? Otherwise, we can say that the limit of d of t is 0, the limit of d of t is 0, or d of t approaches 0 as t approaches t1. Okay. So mathematically in general form we can take a function f of x and a be any real number, a is any real number and x is our variable, we all know that. So how can we write this? As limit x tends to a, fx will tend to a value, definite value L. Alright. So here in some textbooks they use LT, in some textbooks they use LIM. It's up to you, whichever you want you can use it. So limit of f of x when x tends to a is equal to L. L is a finite value. It's a finite value. It should not be an indeterminate form. You studied in class 11. See, infinity power infinity or 0 by 0. These are indeterminate form. There are many, but just I am showing 2 examples here. So you should not get these type of values. Okay. So it should be a finite value. Okay. We can reach this destination either from this side, left side, moving from left side, or we can from the right side also we can reach this destination, isn't it? So we can approach this value from either side. So if you take the real number line, this is 0 and this is 1 and this is minus 1. If you want to reach this 0, you can move from minus 1 also, and or you can move from 1 also, isn't it? So approaching 0. Please take note of this word, approaching 0. We are not reaching the 0. Okay, we are not going to take this 0. We are not going to hold this, own this 0. We are just approaching. For example, if you take a function as fx equal to x plus 5, x is moving towards 1 from the left side. So it will be like if you take 1, suppose for example, it will be easy to understand for this function. So I am taking 1. Okay. So this is, it can take 0.9, right? Or 0.99, 0.999 or 0.9999. See? It is not equal to 1. It is just approaching 1, isn't it? What will happen to this fx? So it will become 5.9. This is 5.999, 5.999, and this is 5.999. So we can guess this fx is approaching 6. Yes or no? So we don't say that x is taking the value 1. It is not achieving the value 1. It is just approaching 1. All right. So then what will happen to from the right side? So right side is, for example, 1.2, 1.1, 1.01, 1.001, right? It is also approaching 1 from the right side. Therefore, this fx will become here 6.001, 6.01, 6.1, 6.2. So from the right side also it is approaching 6, and the left side also it is approaching 6. So we can approach the value from either side. Therefore, there is a left limit and also the right hand limit. So this is from the left hand limit, we write it as limit x tends to a plus, if you a minus, left side minus value, it is less than the value which we take on the real number, therefore you put minus here. So fx, and the right hand limit we write it as limit x tends to a plus, because it is greater than a, we are approaching a, right? Therefore a plus fx. When we say that this limit exists, only when this LHS is equal to LHL equal to RHL. Okay, if LHL is equal to RHL, then we say that the limit exists. When LHL is equal to RHL, the limit exists. For example, if you see the graph, you will easily understand. For example, this graph y equal to fx is drawn as like this. Okay, y equal to fx. Suppose if you are reaching this point, x equal to a, right? And this is x equal to a, right? Here x equal to a. This point will be a comma fa, right? So you can approach this value from the left side. So you can move on the graph from the left side like this, but we are not achieving the value, right? This is left hand limit, and here you are approaching a to get fa from the right side, but you are not achieving that value, right? You are reaching, coming closer, but you are not achieving this value. So in this case, LHL is equal to RHL, because both the sides are approaching the same value. Therefore, we can say that the limit x tends to a fx exists. All right. Okay. Here the left hand limit and the right hand limit approaches the same value. Therefore, we can say that the limit exists. For example, here if you see this graph, the left limit approaches to different value and the right limit approaches to different value. Therefore, here this left hand limit is not equal to right hand limit. Therefore, we can say that the limit does not exist here. Okay. The next topic is continuity. So what is a continuity? By dictionary meaning also you can easily explain what is a continuity. But geometrically we can say that if you say that the function fx is continuous at a point, say x equal to a, if we can draw the graph of this curve, please listen carefully, if we can draw the graph of this curve without lifting the pen from the plane of the paper. Okay. For example, if you can see here, I can draw this graph without lifting the pen, isn't it? So I did not take out my pen and then draw it again, isn't it? But here, if you see this graph, see, I have drawn like this, and then again, see, I am taking out my pen from the board, then drawing back. This also represents a curve, isn't it? But here, this is continuous and this is not continuous. This is geometrical meaning. By definition, if fx is a real function, then y equal to fx is continuous at a point x equal to a. If we say that it is continuous, if limit x tends to a, fx exists and also f of a, and it is equal to f of a. And also the limit is equal to fa. Okay, the limit also should exist, that is the right limit and the left limit both should be approaching the same value. Also at that point, see, suppose this graph, this left limit approaching the same value and the right limit also approaching the same value, and at this point also should be equal, then all coincides, right? Then only we say that the function fx is continuous at this point x equal to a. Okay, so if you say that fx is continuous at the open interval AB, if it is continuous at every point of AB. Okay, each and every point in this interval it should be continuous, then only we can say that the function is continuous in this interval. And if you take the closed interval, we all know it should be continuous at the extreme points also. If it is continuous at every point of AB also and continuous at A and B, the extreme points also it should be continuous, then only we can say that it is continuous on this closed interval. Okay, the function, if we simply say that, here we are mentioning a point here, right? If you simply in whole, if you say that the function is continuous, if it is continuous everywhere in its domain, then only we say that the function is continuous. Suppose the function is not continuous at x equal to a, we can simply say that it is discontinuous at x equal to a, and this point x equal to a is called the point of discontinuity. That's all about the continuity. We are not going in detail about this continuity again. And now our next topic is differentiability. First I will give you the mathematical definition. Let fx be a real valued function. You know what you mean by this real valued function, isn't it? That is, the range is the set of all real numbers or its subset. Real valued function. And a, b, any real number, then fx is said to be differentiable or derivable at x equal to a if limit x tends to a, fx minus fa whole divided by x minus a exists, and it should be finite. It should not give us an indeterminate form. It should be existing, and also we should have finite. It should be finite. So the limit x tends to a, fx minus fa by x minus a. When we have limit, of course we will have the right side and left side limit also. So if you put x equal to a plus h, so you will get the right limit. That is, right limit we put like this, r f dash of a, because we are finding at the point x equal to a, right? So you can replace x with a, that is equal to limit h tends to 0, f of a plus h minus f of a by a plus h minus a. So this 2 gets cancelled, you will get h only, right? Okay, then what will happen to the left limit? So put x equal to a minus h. So L f dash of a is equal to limit h tends to 0, f of a minus h minus f of a by a minus h minus a. So this gets cancelled, you will get minus h in the denominator. Okay, when we say that this function is differentiable, r f dash of a should be equal to L f dash of a. then only we say that the function is differentiable at x equal to a. If this is not equal, then we say that it is not differentiable at x equal to a. Okay. Then if you take a function y equal to fx, if it is differentiable, then how do we denote its derivative? Okay, derivative, that is either dy by dx or dfx by dx. Okay, we are deriving the value of y with respect to x, or f dash of x, or y dash, y1 or d1 dy. Alright, so in any of these way you can represent the derivative. 1, 2, 3, 4, 5, 6. There are 6 ways to represent the derivative of fx. Alright. Okay. Then the process of finding the derivative of a function is called a differentiation. Similarly, how we have learned for the interval a, b, if we say that the function fx is differentiable at this open interval a, b, if it is differentiable at every point of a, b. Right? And for what about this closed interval? It should be differentiable at every point of closed open interval a, b, and also this r f dash of a and l f dash of b should be existing. Okay, then only we say that it is differentiable at this closed interval a, b. See here, right side of the limit and here left side of the limit, both should exist. Then only we can say that the function is differentiable at this interval a, b. Differentiation is mainly to study about how things change, or we can say that the differentiable, by the differentiability we cut something means function, isn't it? So something into small pieces and study about how things change. This is what we study in this differentiability. Or we can say this one dy by dx as rate of change of y with respect to x, rate of change of y with respect to x, or derivative of y with respect to x. Don't get confused. Dy by dx, dfx by dx, f dash of x, y dash, y1 dy, all are same. In the next session, we will learn what is the relation between the continuity and the differentiability, and also the geometrical interpretation of differentiability, and we will see some methods by solving by chain rule, parametric form, using trigonometric functions, inverse trigonometric functions, and higher order derivatives in the coming sessions. If you have any queries, you can mail me at this address, or you can send the WhatsApp to this number. Okay. Thank you.